Hello guys, welcome to another video. And today we're going to be doing a nice question that was written in November, sorry, not November but September 2019, okay, in the Northwest. Okay, seems like the Northwest has some of the tough questions. If you're looking at the dynamics from both maths and physical science, they have some of the toughest questions, as well as Gauteng. The other provinces seem to be more friendly to the students. Otherwise, I'm not too sure, guys. This one includes work energy and power, and including the work energy theorem, so to speak. So I'm not too sure if this topic has already been introduced at school or it is still to be introduced. Nonetheless, I just want to show you that this question can be made a little bit more interesting and difficult as well. So not the usual ease of vertical projectile motion. So let's look at this question 3 here, which is a unique friend of ours here. So it says John of mass 80 kgs drops off. Okay, so if it drops off, what does that mean? It means his initial velocity is 0. Okay, off the edge of a 75, okay, a 75 meter high tower with a strong elastic. But now here's the issue. We are so used to inelastic cords. Now we have an elastic cord here instead, okay, tied around his ankles. And then after falling a vertical distance of x meters, and then he passes point A at speed 31 meters per second. That's not quite nice, okay? Just before the elastic cord starts slowing him down. Okay, so what must we do here? Okay, we are told here, ignore effects, ignore the mass of the rope and the air resistance. Okay, so this is the standard question here. So you always get this kind of a question that says ignore the mass and air resistance, so to speak, just saying this doesn't add any mass into the system and that we are essentially in a vacuum. Okay, all right, so let's look at our diagram. What can we say? We can see here clearly that if you're looking at this motion here, right? Think about it. This motion here, from the position of the top of that tower to when he was reaching this velocity at point A, okay? Okay, so this one was a free fall, isn't it? Definitely. Hey, this thing. Why are you all of a sudden doing things? Hey, this thing. Anyway, so I don't know what happened, but I think it's my hand touching things, and then now they're starting to not be happy. So we can see here that we're doing free fall here, okay? And then of course you know that with free fall we're talking about G equaling 9,8 meters per second squared down. That is an important piece of information that we need to keep in mind. Okay, so until point A we were doing free fall because this rope was not really doing anything to him falling off. But now when he gets to this level, from A to B, no, not coming out the way I want. I went to Tingo. Hey, hi, this thing. Okay, And then now, in this instance right here, we can tell that, okay, now this rope is doing its own things, right? It's definitely going to slow him down. So here we are not doing a free fall. Okay, so it's not a free fall there. Now these are some of the things you want to keep in mind as you work out this question. It says, now explain the term free fall. Basically, a free fall is motion of an object, okay, under the influence of gravitational force only. Okay, so it is motion of an object under the influence of gravitational force only. So that's an easy 2 marks. Next question, use equations of motion to calculate the distance x that John falls to reach his maximum velocity of 31 meters per second. Okay, this is easy because we've got we're looking for the displacement, so this formula becomes nice. The final velocity squared equals initial velocity squared plus 2g delta y. Okay, so this is easy because we're doing a free fall in this instance. We can use g as the acceleration. Now, what is the final velocity? It's 31. By the way, choose a direction. Okay, we're choosing down as positive. So 31 squared equals, this was 0, plus 2 into 9,8 delta y. Okay, therefore delta y is going to be 31 squared divided by 2 into 9,8. Okay, always try to make sure your steps are simplified to some extent so that you don't experience too many issues as you work through these questions. Sometimes it can be a nightmare. So I'm getting a 49,03 meters. Okay, remember this is a distance, so we don't have to worry about direction. It's a scalar quantity, not an issue for us. Okay, so we're going to have a formula there, substitution, and the answer. Okay, great. So next question says, okay, now the rope stretches 10 meters before John stops. Okay, so if he stops, what does that mean? If he stops, it means his final velocity at point B is essentially going to be 0. Okay, now the lowest point of his movement. Okay, at the instant he stops, okay, his camera with a negligible mass drops out. Of course, negligible is too small to be noticed. Drops out of his hands. Okay, but now here's another thing. How is this thing leaving him? It's dropping. Okay, if it drops, yes, it's this thing. If it drops, it means the initial velocity of the camera is 0 as well. Okay, so these are some of the things you want to make sure you put into perspective. Then now the elastic cord pulls John up, so it means it's applying a force on John. Okay, John passes point A with a speed of 25 meters per second. So from 0, he has attained a speed of 25 meters per second on his way up. Okay, great. Now it says calculate by using energy principles only John's average acceleration on his way upwards from B to A. Okay, easy stuff. So 3.3, we're going to answer it this way. Now we want to calculate the acceleration. So what is important here, I always draw myself a force diagram. Okay, of this force diagram of John, I know there's weight directed straight down, okay, which is Fg, and then there is going to be the force by the rope, isn't it, that's pulling him up. And if it is pulling him up against gravity, this force is greater than gravity. So we can say this is the applied force by the cord, gravitational force. And then this is going to span only, this one will only span 10 meters. Okay, because the distance between so as you can see, this only spans 10 meters. Why? Because from B to A is 10 meters, isn't it? So this rope, once we get to point A, this cord will no longer be applying a force on him. So essentially from A upward, he will be doing a free fall. Okay, because you can see that is the origin of a free fall. So this force only acts between A and B. So that's the most important thing. Now we are saying, okay, we want acceleration, but now what comes to mind when we want acceleration? Think of Newton's second law. It says F res equals ma. This is how we can determine this acceleration. But now, what in this formula? What in this formula? Okay, what in this formula is going to be helpful is to find the resultant force, isn't it? Because we've got two forces acting opposite, the gravitational force down, the applied force going up. So what is responsible for the movement upward is the resultant of these two. It's not this one alone. Okay, it's the resultant. So we want the resultant force. Now in terms of energy principles, we know that we know that the total work done by a resultant force is going to be equal to the object's change in kinetic energy, right? That's the work energy theorem. And then we know that work itself in this case is by the resultant force multiplied by delta y, because we know we're doing vertical motion, times cos theta is going to be equal to half, okay, maybe let's write it like this, half m v final squared minus the initial velocity squared. Great. So this is how you set it up, and then we can continue to imply what we want to imply. We don't know the resultant force, but we know that the displacement is 10 meters, but this time we're moving upward. We're moving upward. So since we chose down as negative, okay, so since our downward motion is negative, again, always indicate it every time you're answering these questions, because if you don't, it's going to hurt. So this time up is negative, okay? Cos. Now what is the angle between the resultant force and the displacement? They are both directed upward, isn't it? So the what you call the angle between them is 0. And then this is going to be essentially 0,5. Okay, into his mass is 80, into his final velocity is 25. So now this is 25 minus 0 squared. Okay, great stuff. So Now that we've sorted this, we can now find our force. Our resultant force is going to be this expression 0,5 into 80 into, in fact, we can simplify this big bracket now. It's going to be just minus 25 squared. Okay, divide by minus 10 into 1. Remember, cos of 0 is 1. Okay, let's find our resultant force here. So we've got 0,5 into 80 into 25 squared. Divide by 10. So this is basically minus 2,500 newtons. Okay, but as you can see that this was directed upwards, so we can just say 2,500 newtons up. Okay, that's what is important. Now we can safely say then the resultant force, we know that is MA. So that is Newton's second law, as you could see above. I'm not going to explain this, which implies, now we substitute it in terms of its direction. Remember, it's a vector, so it's minus 2,500 into 80A. Therefore, our A is going to be 2,500 divided by 80, which is 31,25. Okay, maybe let's put the sign there. It's going to be minus 31,25 meters per second squared, which is essentially 31,25 meters per second squared upward. Okay, we just want to interpret a little bit of our sketch right there. So that's how you can work through this kind of a question. Usually you get a mark for your first, and then the general substitution here, and then we can mark, the intermediate answer, and then we mark the final answer. So this is 1, 2, 3, 4, which was the number of marks in the question. Okay, so we're going to do 3.4. 3.4 says, how long will it take John's camera to fall from point B to the ground? And if you're looking here, this is essentially free fall as well. Okay, because this camera is just falling freely, so it's a free fall, not a big deal. So its acceleration is that of g, it's not the other state here. So we can say, fine, we know that we want time, so delta y is equal to the initial velocity times delta t plus half g delta t squared. Okay, so which implies, now we know that the height of the building is 75. So we already have this 49 and this 10. So we're going to subtract these two to get this height. So we want this height right here. That's what is important. And we can just do a complicated calculation here and say 75 minus 49,03 minus 10 is equal to the initial velocity. Remember, it dropped, so it's going to be 0 into delta t plus 0,5 into, remember this was downward, 9,8, and then we want delta t squared. Great stuff. So maybe let's clean it up a bit just for fun, 75 minus 49,03 minus 10 is what? This is 15,97 equals, this one becomes 0 plus, now 0,5 into 9,8 into, okay, yeah, we stop there. This is basically 4,9 delta t squared. Therefore, delta t is going to be the square root is going to be the square root of 15,97 divided by 4,9, isn't it? Each time flies by foot on gag. Yeah, when 15,97 divided by 4,9. Okay, I'm getting a 1,81 seconds as the answer. All right, great stuff. So this is easy as well. Getting a mark for the formula. We're getting a mark for the general substitution, the mark for the answer. So we're getting 5 marks here. The most important is calculating delta y and knowing that the initial velocity was 0. I think that is where the marks are. Now, the big question. So these questions are usually the hard hitters. It says now, how high above the ground will John be the moment his camera hits the ground? Okay, how high above the ground? So that's just the height. Okay, but now we know that John will essentially be pulled during this time frame when this is falling down to the ground. He's being pulled from B to A, and there he is doing the acceleration we calculated. Okay, but from A further, he's going to be doing a free fall, and that's the height we want, because we already know now that this is 15,97 meters from the calculation we just did. So we just add this and that, and whatever height he will go up for the time frame that the camera is going to be going down. So we need to find out this delta y. What is that delta y? Okay, this is pretty easy. So 3.5. So we can say now, from B to A, what would be the time? We know the displacement, but do we really need the displacement? We don't. We want the time only. So we know that the final velocity is equal to initial velocity plus, this time we're going to write A delta t, isn't it? Because that acceleration is unique. It's just not G, it's A. Okay, this implies what? Final velocity, we were told it's 25, isn't it? Equals, the initial was 0 because he had stopped, plus now into minus 31, comma, what did we find there? 25. Okay, delta t, because we want the time. So we can see there, therefore, that our delta t is going to be equal to minus 25 divided by minus 31,25. Okay, what is that? So 25 divided by 31,25. This is 0.8 seconds. Okay, that's an intermediate answer, right? Now, what do we do here? Well, we also know that by the time this guy reaches point A, okay, he does a free fall. Okay, so now we want to know then what happens to his height. Okay, we can say, oh yeah, let's just say the time he takes now doing free fall. Or should I say, yeah, this thing is hectic, man. But I don't like to make questions to be complicated. But what we know is that then delta y, which is this one here that we're trying to show. What is this height right here? We want to know this height right there. That's the delta y. So let me move quickly so that I don't waste too much time. And then delta y is going to be, oops, not you guys are using v. I'm so used to my old syllabus. V I delta t plus half g delta t. Now we can use g because we know that from point A upward he's going to be doing free fall, okay? And then what we want is this. So what did we know? This was minus 25, isn't it? Delta t. Okay, maybe let's sort out delta t. What is our delta t here? Remember, our delta t is this guy minus this time when he was accelerating due to that resultant force. So it's going to be 1,81 minus 0,8, okay? Great. Plus 0,5 into g is 9,8, and we chose down as positive. And then this one is going to be the same difference, 1,81 minus 0,8 squared. So I'm just trying to shorten things here. So we've got minus 25 into 1,81 minus 0,8, okay, plus 0,5 into 9,8 into 1,81 minus 0,8. But when you're doing a complex calculation like this, you need to be very careful, guys, to not make mistakes, because mistakes do occur here. So I'm getting here minus 20, comma, 25, say 2, because it's an intermediate step. But it doesn't really matter, man. We can say 25 meters, okay? Which we know that this is essentially just 20,25 meters upward, okay? At this point, we treat it as a displacement because that's what it is, isn't it? Yeah. And then now we know that we have found the value of our y. Our y now is 20,25 meters, okay? So now how high is he above the ground during this whole period? It's going to be this one plus that one plus that one. So we can say therefore John is equal to 15, what was that? 15, what? Sorry for this back and forth, 97. So it's going to be all those heights, 15,97 plus 10 when he was doing acceleration due to some resultant force than gravity. And then we add the free fall of the last portion, which is 20,25. Remember, this is a height, so it's a distance, which is not a problem. So we just add these. It's 15,97 plus 10 plus 20,25. So I'm getting, what am I getting here? I'm getting 46,22 meters above the ground. Okay, so these are some of the questions which always regard, or at least demand, a bit of planning, because you can't just jump in. You need to make up something, because it's usually a hard hitter type of question. So we can say fine, formula, and then answer. We're not really going to worry about the substitution at this point. And then here, what are we interested in is this height right here. How many marks were we getting, by the way? 6 marks, okay. definitely there has to be some substitution. You can choose this one, but I think the one that is tricky is not up there. But what I think is tricky is this time right here. That time is important, and then we can say the general substitution at this level. So we've got how many marks? 1, 2, 3, 4, 5. And then that's the 6th mark. So that's how you make those 6 marks. Okay. So let's do the last question, guys, and end this pain. Now we're told John eventually comes to rest. Okay. At a distance of 50 meters below the top of the building, or the tower, sorry. And then John is pulled up by an electrical motor at a constant velocity of 2 meters per second. So this is easy, guys. It's not a big deal. Remember, to answer 2.6, we know that at this juncture, if we're doing a free body diagram, John is actually having 2 forces acting on him. And these forces are roughly balanced if you think about them. Because this is now going to be the applied force by the engine or the motor. Maybe let's just say Fm, force of the motor. And then this is the gravitational force. And he is himself 80 kgs. And then we know that John is going to be pulled up for a displacement of 50 meters. Okay. So that is very easy. So now we're looking for power. So we know that power is effectively the force. It depends on the force that we're looking for. So it's going to be the force multiplied by velocity. Let's just say Fv. Okay. And then what do? We know that he's doing constant velocity. It means the resultant is 0. So those forces are perfectly balanced. All right. So now it means that force of the motor is basically going to be essentially the force of gravity. So this is going to be mgv, which is going to be 80 times 9,8 times 2, which is that velocity. And then it's 80 into 9,8 into 2. Okay, so we're getting 1568. Is it watt or watt? I think it's watt. It's watt. It's a watt. No, we don't need to write in words. The symbol is good enough. Okay, not a problem. So guys, you're getting a mark for your formula, substitution, answer. So this is how this kind of a problem could be approached. And then of course, look at many ways you can look at this, but this is just the simplistic approach I could give to you guys to ponder upon. And please do keep kinds of questions like these ones in mind. They create a bit of a problem for someone who's not suspecting, but at the same time, they are quite good to ask students, because you get used to say this one is projected upward and then it hits the ground and then that's it. There's no other force. So here there's a bit of dynamicity in terms of there's an involvement of an external force, and that force only acts for a certain period of time and then it's gone. Okay guys, I hope you liked the video and that you've learned something as well. And let's keep the train moving. I'll see you on the next one. Like I promised, I'm going to do a short course on sequences and series for maths. So I'm going to start with the quadratic together with the arithmetic sequence, because those two are somewhat related. And then the second part of this will be the geometric sequence and the convergent series, okay, or sum to infinity. And then we should be at least in a position of getting a distinction in our term 1 exams. So I hope you guys are gonna go get it for me and for yourselves. Bye-bye.